All right, in this section, I'm going to be demonstrating how to obtain control coefficients, specifically digital control coefficients, for the STM32 microcontroller implementation of a closed loop control system using the buck converter, of course, for the buck converter, which is a power electronic converter in this instance. Um, so first off, the first thing you want to do is the input voltage. You want to initialize the converter parameters, which in this case, of course, is a buck converter. So you want to initialize the control, the converter parameters, which is the input voltage in this case, the output voltage, output current, output impedance, the switching frequency, and these four values right here are the parasitics. So here you have the parasitic resistance of the inductor RL, for the capacitor RESR, and the next one you have here is the so basically when the MOSFET is turned on, there's a voltage drop across it all the time. Most of the time, there usually is one. And here you have the V forward, which is for the diode when the diode is forward biased and conducting current. It does have a voltage drop across it as well. It's important to note that from my experience, these values, if you design your system very well, though, they're often negligible, not entirely negligible, but have very little effect on the outcome of your system. But it's good design practice to always include them in there. And next, you have the inductor current. In this case, the average inductor current is equals to the average output current. And of course, you have the duty cycle, a calculation of the duty cycle. And always in this case, of course, you can calculate the inductor, the required inductor and capacitance value from scratch. But in this case, I decided I already chose these values. So I'm just going to input them there. Of course, if you want to calculate them, you can just uncomment that. These two lines, which is calculating for the inductor and the capacitor. And of course, I just want to state specifically this software before I carry on. This software using in this case is being used is Octave, which is, if you don't know, it's sort of like a free version of MATLAB. Basically, most of what you can implement in MATLAB, you can implement in Octave. So I do encourage you to try it out, and it's totally free. I actually think it's open source. I'm not entirely sure about that, but from my experience so far with Octave, there's certain slight differences here and there, but it works out really well most for the most part. All right, so the next step after initializing everything, of course in this case I chose 200 microhenries rather, and 440 microfarads for the capacitor. And next step, you actually want to initialize the crossover frequency. So this is very important in controller design. So in the approach I chose the phase margin approach. Of course, you could choose other approaches such as you wanna focus more on the settling time, and the rise time, etc. You should note that in terms of control design for power supply specifically, you're mostly going to be dealing in the frequency domain. So you want to focus on that in your design. In other aspects, I guess sort of like DC motor speed control, for instance, you might be focusing more on rise time and all those other parameters, time-based parameters. But in crossover frequency, excuse me, in power supply design, you want to focus more on the crossover frequency. So in power supply design, you want to focus more on the frequency domain. So in this case, what you have first, in this case, you want to define your crossover frequency. As I explained earlier on, um, I sort of want to focus more on, in this case, with this particular converter, I sort of want to make it robust. So I'm not gonna make the crossover frequency higher than the resonant frequency, for instance. That's classically what you should do in terms of making something for a specific application. Think of a power supply for um for an MCU, perhaps for a processor in a computer, gaming processor, for instance, GPU specifically. you want to have a really high crossover frequency and really high response time. You need the disturbance response to be very sharp. But it's also important to know that if you have a really high crossover frequency, your converter is very prone. It's very sensitive, so it will respond to basically anything as quickly as it possibly can. Um, so so that's basically what you get in that instance. But in this case, I'm not really worried about disturbances in this case. Lots of disturbances. So I'm sort of focusing more on robustness, i.e., I could change the set point, and it won't affect the system drastically, if you understand what I'm saying. It won't make the system unstable. So I'm focused more on robustness in this design approach, basically. Not to go too much into theory, but just to give you an idea of why the crossover frequency is so low. Well, this is the crossover frequency in radians per second for the current, specifically for output current to duty cycle specifically. And this is the crossover frequency, FC. And then you have the crossover frequency for the complex, I. And that's what you have there. And next you have the same thing, crossover frequency for the voltage in radians per second. I decided to make them the same in this example to not, complicate things a little bit too much. The same thing here. This is the crossover frequency in hertz, and this value here, these two lines here, I'm actually going to explain further later on. This is important to actually get the gain in phase, but I don't want to talk about it yet. But that's why these two values are necessary. And of course, you want to define the target phase margin for your output current to duty cycle transfer function. And here you want to define your phase margin for the output voltage to duty cycle transfer function. And next, you actually define these transfer functions in the code. You have to do that. And then this is essentially just the way it is when you write it out. It's basically just defining the transfer functions for the current, output current to duty cycle, and your output voltage to duty cycle. You want to define both of them, and that's basically what you have there. And next, you actually want to get the gain and phase at the crossover frequency, at the desired crossover frequency. The gain, you want to get the gain value, and you want to get the phase value as well. So basically, that's what this is here. So first off, this is the first part. This is actually where that particular variable comes in. So in this case, what you're doing here is you're basically taking that value, you're taking 7766, and you're multiplying it by an imaginary number. And you're just gonna input that into the transfer function. You're gonna substitute that into the transfer function where S goes. Of course, I'm already using the S variable in this code, so we're using the G in this instance for that value. It's some weird thing with Octave where you have to actually do that. But anyway, you have that, and then what you're gonna get as an output here is actually an imaginary number, which is what you want, and then you can split that up into the gain and phase components, which is done later on. So first off, you do that for the current transfer function, and then you do that for the voltage transfer function. Obviously, the difference between these two is the presence of RO for the output voltage due to cycle transfer function. And next, this is actually where you design the controller. And of course, the first thing you want to do there is you want to split it up into the gain and the phase values. So for the gain, I'm talking about this equation right here. So to split that up into the gain, you just take the absolute value of that value, and then the next, to split it up into the phase, you do this. And I actually want to do this for the purpose of this part is a little bit redundant. So it's a little bit redundant because I actually converting it to degree here, and then I'm taking it back to radians, but not to worry about that. The most important aspect is basically what you're doing is you're getting the phase. You're getting the phase of this particular value here. and that's actually important to determine the amount of phase compensation you require. That's the purpose of this, basically. So first off, you want to define your target phase margin in radians, and then you actually want to calculate the phase compensation that you require, which is going to be the target phase margin minus the phase minus 180 degrees. So if you actually go and check out how to calculate the phase margin of a Bode plot, that's exactly what this is. To get the phase margin of a particular Bode plot, that's exactly what this is. Um, and basically what we do in this case would determine what phase compensation do we require to hit our target phase margin. So anyway, that's the equation for that. And next, what you want to do is you actually want to calculate the parameters of your compensator transfer function. So this is your compensator transfer function. Of course, the parameters are the kpi and the omega I in the case of the current, and here you have the kpv and the omega iv, because I is actually an integral component. Um, and and then basically what you want to do after that is you want to calculate your kp after you obtain the fi value, which is the omega I in this case. Sorry, which is going to be used to calculate the omega I, but it's fi in this case. You want to calculate that, and you also obviously get that from the crossover frequency. And then once you calculate your KPI, you're sorted on that front. And then you calculate your omega I, you're sorted on that front. This is exactly like it is in the this is just the way it is to calculate for this particular compensator. And also, fun fact to note is this line here, of course, tells you the amount of phase compensation that you require. And the sign of this would actually tell you what kind of compensator you need. So if this value was negative, if phase comp I was negative, you'd actually design a lag compensator. A lag compensator will suffice. But if this value was positive, you would actually need a lead compensator. But in power supply closed loop controller design, digital control loop design for power supplies essentially, lead compensators are often impractical. They're not very practical to be utilized in this scenario. So what you actually want to do is use a lead lag compensator. So in digital control systems, lag compensators are very much favorable. They work out very well. So in the case where you actually need a lead component there, where you basically just need positive compensation, you actually should implement a lead lag compensator, not just a lead compensator. Um, I suppose in some cases lead compensators have worked, but in my experience, they usually don't work very well for power supplies. Anyway, that's what you have there. And you do the exact same thing for the voltage. You get the V gain using this specified transfer function, and you get the phase, and then you obtain your target phase margin in radians for the next step, and you actually obtain the phase compensation you require. Subsequently, you obtain the frequency, the integral frequency here, well, for the parameters anyway, and then you obtain your KPV as follows. I really don't want to talk through complicated equations. It could get a bit confusing. I find it best for you to sort of just look through that yourself and find your way through it, essentially. In this case, it's what it is on the screen. Of course, you utilize the crossover frequency and the integral aspect as well. And then, of course, at the end, you obtain omega IV, which is important. And this is the final transfer function, of course. And basically, everything we're doing in this particular sequence, this octave sequence, is to obtain these coefficients, right? These coefficients, the specific coefficients. And of course, afterwards, that's the TI. You can do the Bode plot and actually check that the crossover frequency meets up with it, which is what the next sections of code do. So this is what you have there, and you have the margin I. This is actually shows you that you obtained your current phase margin, current gain margin, phase margin, crossover frequencies in the phase, etc. And you do the exact same thing for the voltage aspect. And now this next part is very important. It's absolutely crucial. So in this case, in closed loop control systems, you're basically updating the duty cycle in intervals basically. So in this case, I was updating every 100 microseconds. Of course, you could go down as low as into the nanosecond ranges, of course, but in that case, you really need to optimize your code. The code needs to be optimized for that particular function. In this case, I sort of used a lot of floating point values, which took a lot of time, but I think it worked out all right for this particular scenario. So what you want here is it's a time of 100 microseconds. Of course you could do 10 microseconds, but what this particular line of code does for you is it actually gives you the coefficient from your transfer function, which is in this case GCI and GCV. It actually generates that for you, which is crucial, which is super important and so valuable in this case. So it does that for you. And in this case, of course, if the time you were so the closed loop controller code, if you implementing that every 100 microseconds, then this is perfect. If you're implementing it every 10 microseconds, what you want to do is change that time to 10 microseconds. Sorry about that. Of course, if it's 20, you change that as follows, etc. Of course, it's 100 microseconds in this case, and I'm just going to leave it at that. And basically, that's the code for the well. I use the word code loosely because this is Octave. It's more of a sequence. Um, so basically, that's what you have here, and I'm gonna run it. I'm gonna pop over to the command window, and of course, that's what you have here. So as you can see, you have the current gain margin, which is 17.66 dB. It's important to note that I did not focus on gain margin in terms of the design in this aspect. I sort of went for a gain of 1 in the controller, which basically means I don't want it adding any some. By gain I mean if I have a set point, if my set point is perhaps something like 17 volts, I don't want my output to be 34 volts, if you understand what I'm saying. If the set point is 17 volts, I don't want an output of 34 volts. I just want it to be standard. So I wasn't focusing too much on that other aspect. So you have the current gain margin, you have the current phase margin over there, which is 89.9, which aligns with what we're designed for. And you have the crossover frequencies over there. That's for the gain. That's the gain crossover frequency. And here you have the phase crossover frequency. In well, this should actually mean radians per second, but anyway, but you understand what's going on there. And the same thing for the voltage, exact same thing. Phase margin 89.9, and that's about it. And now for the most important part, you actually want to get the control coefficient. So you say GID, and then you have GVD. All right, so these transfer functions, so this transfer functions is what you actually use in your code. I'm going to show you how just now. Let me port over to the Word document. All right, so this is the transfer function obtained. Specifically, this is for the voltage, I believe, or this is for the current. My apologies, this is for the current. So this is the transfer function obtained for the current from Octave. So this is the standard form. Right here you have the standard form. Essentially what you want to do is you want to take this, you want to convert this into the standard form. You want to transform this into the standard form. And that's what you did in the next stage. Of course, the taking it from this to the standard form is you basically divide both sides, the numerator and the denominator, by z. And in that case, you get this, you get it in standard form. And once you compare it to what the standard form is, you actually realize that BO is this value right here, and then B1 is this value right here. And that's what you obtain, and that's basically what you have for this particular system. You have B1, and then you have BO. And then next, you actually have for the voltage transfer function. Let me just go back to Octave very quickly. For the voltage transfer function, that's what you have there. That's the transfer function given right here. I was just going to go back to the Word document, right? So that's the transfer function obtained for the voltage loop. Let me not say voltage loop. Let me say output voltage to duty cycle transfer function, because stating voltage and current loop sort of specifies something else entirely, which is double loop control, which is something else completely. Anyway, this is what you have for this particular system, and again, what you want to do in this case, you want to divide the numerator by z, denominator by z. And that's what you have there. And then comparing that to the standard form, you find out that BO is this value, and then B1 is this value right here. And that's essentially it. That's basically how you obtain the control coefficients to be used. That's how you obtain the control coefficients basically for your system. And yeah, there's really nothing else to it. So before I carry on, well, actually, this is the end of it. I sort of just want to do a brief overview of everything. Okay, let me go back to the editor. So the purpose of everything is, first off, to obtain the transfer function, the specific parameters for the transfer function for the compensator. In this case, for a lag compensator, I chose a buck converter because most often they're very easy to control, and with lag compensators, they're very easy to control buck converters using a lag compensator. So in this case, the first thing that you want to do is you want to initialize your converter parameters, and that's basically what you require. In short, your output voltage, your output current, and your output impedance, basically your output power that you require, and your inductor and your capacitor. That's the main aspect of it. Everything else is pretty much parasitics and calculating your the duty cycle, which is more useful to calculate the inductance actually. The required inductance. And next, you actually want to initialize your crossover frequencies. For both the current and the voltage, you want to initialize those, and your target phase margins for both the current and the voltage. And next, you want to define the small signal transfer functions. And after you do that, you need to determine what the gain and phase are at, what they actually are at your desired crossover frequency. And then once you do that, you can actually calculate your phase compensation required. And then the phase compensation required will actually tell you if you should use a lead lag compensator or a lag compensator. In this case, it should be noted that this code is specifically for a lag compensator. For a lead lag compensator, you're going to have to design that very differently. This is for a lag compensator. Anyway, so you have this. So once you do that, you can actually calculate the parameters pretty easily from that point on. So this Fi, and you have the Kp, and of course you want to obtain your omega I values. And you do the exact same thing for the voltage transfer function. It should be noted that these transfer functions are basic, are the normal small signal transfer functions relating output current to duty cycle, in this case output voltage to duty cycle. They're the standard transfer functions. And once you have that, and you go into the next stage, and the next step, of course, is defining the compensator transfer functions. And then after you get that, you can actually do this to actually plot your Bode plot. It's quite a lengthy process with an Octave, so I just commented that out because I don't need that for this particular example. And of course, you want to define it, and this would actually show you if you hit your targets, your margins that you actually wanted. And the next thing, this is actually quietly the most important part of the code. I should put that separately. Yeah, the cool. And then that's what you have here. All right, and this is for the current, and this is for the voltage, and of course the 100 microseconds in this case is of course the sampling time. I think let me just specify that TSI and TSV so that it makes more sense that way. Right, there you go. And of course, let me just change that to TSI, TSV, TSV. And that's basically it. There is nothing more to it. And then once you obtain it, you compare them to the standard form and you obtain the coefficients right out of that. But this actually gives you what those coefficients would actually be. Um, and that's that. Yeah. And then you just type that into it. Of course, it should be noted that this could be implemented in MATLAB as well, but in some sense, I actually like Octave because it's free. That's the main reason I like it actually. Um, and the amount of effort put into it to actually make it work out as well as it does. For a brief between MATLAB and Octave, you just need few differences here and there, but I think Octave is a pretty um good tool to actually obtain this. And yeah, it has a lot of other functionalities as well. But anyway, this is not an ad for Octave. But my point is, this is basically how you obtain coefficients. Of course, you could use the other methods, which are quite tedious and very prone to errors. So I strongly recommend that you use this method to obtain the coefficients. Um, anyway, that's about it. Um, I'll see you in the next section. Cheers. All right. Before moving on to the next section, I sort of want to address this um output current here. I just want to state which is obviously different to what was stated in the previous section. I just want to state here that it doesn't have a large effect on it because this system is designed to be robust, i.e. the output current set point could be changed in the firmware as you would like and as you like, and obviously within a reasonable range, but and it will not make the system unstable. So essentially I just decided to do it in this way, make this 2.125 and the other 2.133 to sort of actually see how robust the system will be if I design something for 2.125 and have a set point of 2.133. What effect will that actually have on the system? And as you will see in the later sections, it actually gives the results that you might think it's a robust system, and it allows for that. Um, it allows for that, especially with the design of the the chosen phase margin in this case. And in essence, what I'm trying to say is not to worry about this value deviating from the 2.133. Obviously, they're close, but they deviate a little bit. But not to worry about that. Everything is to plan, and it's not something that you should worry about being having a huge effect on your controller. Of course, in your application, you can just have them the same. But all right, that's about it. Yeah. All right. I'll see you next one.